right,
Yeah.
we will get this show on the road. Very good. So, is all the notes and all the videos are posted. You can always find them on YouTube, even if I haven't posted a link. So, they're being put on for the secret YouTube channel. Right. So problem set 2 is due by the end of the day today, and problem set 3 is now available. Yeah.
The podcasts are on YouTube? Will we get any of the ad revenue?
If I would, I wouldn't be driving that Toyota. I love my It's the best car in the world. Really. Anyway, yeah.
I noticed problems at 1 solutions. I don't think they're up yet.
I just put them.
Oh, you just. Oh, I'm sorry.
Yeah. I just put them out there. Yeah. Well, before.
Yes, it was supposed to.
Yeah. I'm being fact checked. Free Pinocchio saying put the solutions out there. All right. Yes.
Will a new Dropbox be added, or do we
Use the same one. Use the same one. Yeah. All right. Good. So last time we were discussing the dynamics of a qubit, and as we've said many times, a qubit is a two-level system which is isomorphic to the physics of spin 1/2 angular momentum. So the dynamics of a qubit are the dynamics of a spin 1/2 angular momentum. And so we wanted to review the dynamics of a spin 1/2 angular momentum. And that dynamics there's nothing more than the dynamics of a magnetic dipole moment in a magnetic field. So the dynamics of a qubit are isomorphic to the dynamics of a magnetic dipole moment in a magnetic field, okay? And so that quantum mechanical dynamics is actually equivalent to the classical dynamics of a magnetic dipole in a magnetic field. So we quickly reviewed that. So we think about a particle that's like a spinning ball of charge, has an angular momentum and has a magnetic dipole moment. They're proportional to one another by what we call the gyromagnetic ratio. And the energy, if we have an external magnetic field, the energy associated with, let's say the magnetic field is a static magnetic field in some direction, then the energy is mu dot B. And if we write mu in terms of the angular momentum, then it can be written in terms of an angular velocity dotted into magnetic field. That angular velocity vector is minus gamma B naught, okay? And the dynamics of the angular momentum is determined by the rate of change of the angular momentum, which is the torque. And the torque vector is given in classical E&M by mu cross B. And so again, if we express mu in terms of the angular momentum vector, it's omega cross L, okay? And that is the dynamics of a gyroscope. And so what will happen if you have some initial angular momentum vector and you're in this field and a magnetic dipole moment, the angular momentum and the magnetic dipole moment will precess around the magnetic field in the absence of any other damping forces at the Larmor precession frequency. So this is what's called Larmor precession. Okay. Now, a very important phenomenon that will be the heart of so much of what we're going to talk about is equivalent to what's the problem of what's called magnetic resonance. Okay. So in magnetic resonance, the idea is that I have some strong magnetic field, many Tesla, sitting in my MRI machine, and my protons are spinning around at some resonance frequency, and I want to see where the protons are, so I'm going to resonantly flip them by applying an oscillating field that is transverse, perpendicular to the direction of the static magnetic field. And we can get resonance if we rotate that magnetic field with the precession, the natural precession frequency. And the classical dynamics of that, we can go to the frame that is co-rotating with the magnetic field, because if I'm in the frame that's rotating with the magnetic field, in my frame, this field is static. And if this thing was precessing naturally in B naught at frequency omega naught, then it will see a static magnetic field, and it will precess around that transverse field. Okay, that spin, or it's just magnetic resonance. Okay, and the equations of motion that describe it are simple. We go into the co-rotating frame. In the co-rotating frame, this field is static, so the B perp is static, and it's got some magnitude. And it would be, if I'm in phase with it in the x direction, in the co-rotating frame, if this is the x direction. This is the field in the co-rotating frame, it's static. But because I'm in a rotating frame, I have to add the Coriolis force, which is like a pseudo-magnetic field. It's like adding, it's as if there were an additional longitudinal magnetic field that I have to subtract out. Okay, so omega here is omega in the z direction, because that's the axis of rotation of the frame that I'm going into. I'm going into a frame rotating around the z-axis at the frequency of the drive. I am driving the system, vroom, vroom, at frequency omega, okay? And so I go into the co-rotating frame at that frequency, I add this extra term, or subtract it, and so the dynamics of the angular momentum vector in the co-rotating frame now is this. So this would be the longitudinal field. I subtract off this, and what's left over is what's called the detuning. How detuned I am from natural resonance. And then I have a precession that torques me around the transverse field. So the total effective precession is around, oh, here it is, I've written it. Has a component that is in the transverse direction at a frequency omega, which is what we call the Rabi frequency, not the Rabbi frequency. He was Jewish, but it's pronounced Rabi.
Was he a rabbi?
There might have been, I don't know. But I would imagine somewhere in Germany he was a rabbi. In any event, we see in the co-rotating frame, we Larmor precess around this vector at a rate that is the square root of this squared plus that squared. That's the magnitude of that vector. And when I'm on resonance, I'll flip from the south pole to the north pole. If I'm off resonance, I don't get all the way there. Okay? And finally, we said, well, I can think about the quantum problem exactly the same way. My Hamiltonian now is minus mu dot b, where b is a function of time, and mu, the magnetic dipole operator, is proportional to the spin. So this is a spin angular momentum, and a particle with spin and charge will have a magnetic dipole moment, and it's proportional with some proportionality constant depending on the particle, okay? And so it's the same problem that we had over here, and what we saw is that the Heisenberg equations of motion, although I didn't exactly do it right, the notes have it right. The whole story about going to the rotating frame will become clearer today. But if we look at the Heisenberg equations of motion, then in the rotating frame, it's exactly the same. So the problem of spin magnetic resonance in quantum mechanics is exactly the same as the classical gyroscope. There is absolutely no difference. Well, as far as its operator equations again. Of course, there is probability and the like. But what this is telling me is that the expected value of the spin angular momentum vector processes exactly like the classical angular momentum does it, in no way different. It's exactly the same trajectory, okay? And in particular, if we have spin 1/2, where the spin angular momentum is h bar over 2 times the vector of Pauli's, then this equation is equivalent to saying that the block vector processes. So although we solved this last time in the Heisenberg picture, we get an equation for how the state of the system evolves in time, because Q is the block vector. Remember, the block vector is the vector of expectation value of sigma x, expectation value of sigma y, expectation of sigma z, which Bloch called u, v, and w. Okay, so that's the mean sigma x, that's the mean sigma y, that's the mean sigma z. And the state of the system at all times is this. Okay. Pause to absorb that. The point we said, any density matrix of a qubit is a half the identity plus a half the block vector. That's what the state of the system is. So if we know what the block vector is as a function of time, we know what the quantum state of the qubit is at all times. And I can think about this instead of this. This is the block vector in the rotating frame. The block vector will undergo this Larmor precession, and that's what happens to the qubit. So we solved it, okay? Now, there's more to understand in this. There's a lot to absorb in this. And I want to go back now and talk about this problem, not in terms of the Heisenberg equations of motion, but in the Schrodinger picture, okay? So let's rewind and talk about these dynamics in the Schrodinger picture. Where I have a state that's evolving as a function of time, okay? And some Hamiltonian. So let's consider first, without the driving, let's just think about free evolution in a static magnetic field. So let's say I have an H0, which is minus mu dot D0. So I have a static magnetic field, let's say in the Z direction. And I want to know, how does the state of the system evolve according to this Hamiltonian, okay? So mu is equal to minus gamma S, which is equal to minus the spin angular momentum is h bar over 2 times the Pauli's. Okay? So again, this is h bar omega naught over 2 dotted into sigma, where omega naught is minus gamma b naught.
Did you put the order of the sigma and the b? Or should I miss it?
Sorry, can you repeat the question?
Did you flip the order of the
I did. I mean, B, this is a vector. I can put this in, put it on either side. It can be, this is a, what in some ancient jargon was called a C number as opposed to a cube number. I mean, God knows why. They were saying this is not an operator, so I can put the B on either side of it. Yeah. Okay. So with this in the Z direction, this is h bar omega naught over 2 sigma Z. So that's the Hamiltonian. The eigenvectors of the Hamiltonian, thus the energy levels of the system, are spin up along Z and spin down along Z. So if my gyromagnetic ratio is negative, then spin up is the higher energy state and spin down is the lower energy state. And the energy splitting, one goes up by h bar omega naught over 2, and the other goes down by h bar omega naught over 2. And so the energy difference between them, the splitting between them, is h bar omega naught. Okay, so those are the energy levels of this Hamiltonian, right? Now, if I start in a state which is not an eigenstate of the Hamiltonian, the system will evolve in time, right? So if I started, for example, the spin of the system along the x-axis, let's suppose, then we know it's supposed to Larmor precess. It's supposed to precess around the z-axis at frequency omega naught. Okay, we can see that in many ways. It's not one way to the Heisenberg picture, but I'm going to do it in lots of different ways. So we can write this. One way to think about how the state evolves in time is to decompose it in terms of the energy eigenvectors, and then put up the phases associated with the different energies. So the energy eigenstates are spin up and spin down along Z. How do I express spin up along X as a superposition of spin up and down along Z? Yeah, but in this case it's X.
Up, down.
One over, so it's cosine of pi over 4 if I like, which is a square root of 2 plus 1 over root 2 spin down along Z. After a while, we just remember that's the answer. But you're right, Benny, in your thinking about it. So that's the state of time t equals 0. The state at a later time is given by the same superposition, but with the energy eigenvalues associated with those two guys. Being very either pedagogical or pedantic, depending on what you want to call me. I'm sure you call me lots of things in front of my back. Anyway, this energy eigenvalue is h bar omega naught over 2. So this is e to the minus I omega naught over 2, and this is the energy eigenvalue is e to the is for spin down is minus, so it's e to the plus I omega naught over 2, right? Those are the two phases. So the state at a later time, given this initial state, I can write as, I'm going to factor it out, an overall phase, 1 over root 2 spin up along z plus e to the I omega naught t spin down along z. Right? Everyone with me? So I just factored out that overall phase. And I don't really care about that, the overall phase of the matter. So now I ask you, in what direction is this, every pure state is spin up along some direction, right? So along what direction is this spin up as a function of time? Well, we go back to what Benny was saying. We remember that an arbitrary state along some direction is cosine theta over 2 spin up along z plus sine theta over 2 e to the I phi spin down along z, where theta and phi are the polar and azimuthal angle that determine the direction of the spin. So what is theta and phi for this state? So cosine theta over 2 has to be 1 over root 2, and sine theta over 2 has to be 1 over root 2. So what's theta?
Theta is 90.
90 degrees, pi over 2, right? Because cosine of pi over 4 is 1 over root 2. So it's in the equator, okay? And what about, what's phi? Omega t. So phi is the angle relative to the x-axis. So what is happening to this spin as a function of time is that we started it along the x-axis, if I call this the x-axis, and it's going to precess, the block vector precesses at angular velocity omega naught, which is Larmor precession. So the spin is precessing, and no matter where I started it, it will precess with that frequency. Okay? So we see the same Larmor precession derived in a completely different way. Okay? Now here's another way we can see that. We also know if I have a static magnetic Hamiltonian, then I can easily write down the time evolution operator and by just exponentiating the Hamiltonian, right? So in this case, we have there is the Hamiltonian, so this is equal to e to the minus I. I'll write it in a couple of different ways. Let me write it as omega naught dotted into s over h bar, omega t. Okay. This is an example, as we talked about, of a rotation operator. The rotation operator in quantum mechanics is generated by angular momentum. So the spin angular momentum vector generates the rotation of the spin. Okay? So this is a rotation operator. Remember, there's various notions of rotations that we talk about. There's a rotation in Hilbert space, because Hilbert space, I can think about rotating vectors in Hilbert space. But I can also think about physical rotations in 3D space, which takes a vector that was pointing in some direction. I create a magnetic dipole and pointing this direction, I want to drive it over there. There is an operator which does that, and that's the rotation operator, right? Now, for spin 1/2, in this particular case, where the spin angular momentum is h bar over 2 times the Pauli's, and for the this in the z direction, this is equal to this. Okay? Now, this is a unitary operator acting on a two-dimensional Hilbert space. And maybe I should just, so an arbitrary unitary operator that acts on a two-dimensional Hilbert space is in the group U2. Okay, I won't make the joke again. The group U2 is the group of unitary matrices that are 2 by 2. Okay, this is in the group U2, but it's special. Why is it special? If I were to write this as a matrix in the basis of the eigenvectors, what does this matrix look like? What are its matrix elements as a 2 by 2 matrix in the spaces? Yes, Tristan?
So it'll be e to the negative I and negative t over 2 in the top left, and then the bottom right, the same thing, but a positive I.
And what about the off diagonal?
0.
Thank you very much. So diagonal matrix in the basis of its eigenvectors, and these are its eigenvalues. And what is the determinant of this matrix? 1. So that makes it special. So these are in the group SU2, okay? Because their determinant is 1. The general U2s would have not necessarily the eigenvalues being equal. When the spin is not 1/2, this will be, say it's a spin 1, it would be a 3 by 3 matrix, but that's called a different, it's also the same group, but it's a representation of the group for spin 1. It's still an SU2 operator, but that's another story, okay? All right, so, yes?
Regardless of the group of the operator, if I want to displace my state, whether I want to displace it in a rotating frame or I want to push the state in time or space, it's just the exponential and whatever.
Yeah, the time evolution operator is always of this form.
Yes.
But for the special case where the Hamiltonians are proportional to the spin components, it's the group, those will be SU2. If I had spin components Sx squared and Sy squared, it wouldn't be an SU2 operator. Of course, I don't have that for spin 1/2 because things squared in the identity.
Thank you.
All right, so another thing to say about this rotation operator, this SU2 for spin 1/2, is that this takes a special form, which is, so in general, if I think about a rotation about axis n by angle circle h, then that is and for spin 1/2, that is that. This factor of 2 is coming from the Pauli's. Okay. Now, for that, this is an arbitrary SU2 rotation operator. An arbitrary SU2 rotation operator is specified by 3 parameters. One way of specifying those parameters is the axis. It takes 2 parameters to specify the axis and the angle. This is the axis angle parameterization. And it has this form. When it's SU2, this has a very special form. Which is this. This is not true for a rotation if it wasn't spin 1/2. but because it's spin 1/2, we know that any operator is some amount of the identity and some amount of the Pauli's. And we can find that by a power series expansion, expanding the exponentials of power series, collecting all the terms, and we get cosine of theta over 2 times the identity, minus sine theta over 2 times the Pauli along the direction of rotation. Yes?
If that S operator was proportional to the Pauli, but instead of by h bar over 2 by an h, would that e to the I be theta instead of theta over 2, or would it?
Yeah, that's right, but it's not, because it's spin 1/2.
In this case, yeah.
And then, I mean, it wouldn't be, you can't have it all, Tristan. You can't have spin 1 and the Pauli's. If it's the Pauli's, it's spin 1/2, and there will be a 2. If it's spin 1, then it's not the Pauli's over 2. It's the Gell-Mann matrices or the spherical tensors or something else.
For photons also, though?
Absolutely. But for, I mean, okay, I don't want to digress too much. The story of the photons is more complicated because we only have 2, it's spin 1, but we only have 2 components for a whole nother reason because it's massless, and we'll come back to that. But at that point, it's a qubit, and when it's a qubit, it's a pseudo spin 1/2. Emphasis on the pseudo. Okay, so, where was I? Yes, I was here. So, right. So when we have the state so this is just another way of expressing, if I have e to the I, so if I have, you know, the time evolution operator that we had just a moment ago for the spin being in a magnetic field along the z-axis, this was the time evolution operator, which is cosine omega t over 2 times the identity minus I sine omega t over 2 sigma z. And if I start the spin along x, it's going to process around the z-axis at frequency, angular frequency omega. Very good. All right, so let's talk about spin magnetic resonance now. It's the same problem. So my goal is, we had this picture over here where we said, I put the spin in a strong magnetic field, and I split the energy levels, I split the degeneracy, now spin up and spin down are separated by this frequency, okay? And I want to flip this to this. Now one way, let's say I started here. We think about this in a picture that's kind of old-fashioned, is absorption, right? I want to put on a photon that has a frequency omega, near omega naught, and I absorb that photon, and it goes from here to here, okay? And the way I would do that, I would say my Hamiltonian, I have my H0, and then I have an interaction Hamiltonian that is oscillating as a function of time. In this case, my interaction Hamiltonian is coming from the transverse magnetic field. And my transverse magnetic field, let's say, has an X component and a Y component. Just as before, exactly as we discussed for the classical gyroscope problem, right? So now my interaction Hamiltonian, when I write this out, is going to be of the following form. When I put in mu is equal to, I can write this as minus gamma b perp got it into the spin, which is equal to h bar times the Rabi frequency cosine omega t sigma x plus sine omega t sigma y. Okay, it's in a similar vein to what we had over there at in the top of the board where we had a static magnetic field along the x-axis. Now we have a oscillating magnetic field that's rotating in the xy plane and oscillating at that frequency omega, where the Rabi frequency is this. Yes, Farouk.
It is very hard to differentiate between the drive frequency and the omega naught.
I'm sorry, you have to
It
speak
is
up.
very hard to differentiate between the
The
drive.
hacks?
It is very hard to differentiate between omega and omega naught, which is the drive frequency and the.
Okay, oh, it's hard to differ. So omega naught here is the splitting that we had at the beginning. We put on a static magnetic field, and that splits the two states, and there is an energy difference. H bar omega naught is the energy difference. We are now driving the system with an oscillating magnetic field, and we can think about there's a photon, if we like, we can think about that, that would be absorbed, and my omega is tuned close to omega naught. It may not be exactly on resonance, it could be slightly off resonance with some difference that we're calling the detuning.
That means the detuning here is going to be very, very small.
Generally, we would assume omega that this is small, that this is close to resonance. Okay. All right, so this is the Hamiltonian. If I'm going to rewrite sigma x as in terms of sigma plus and sigma minus, and sigma y in terms of sigma plus and sigma minus. And when I do that, this now takes the form e to the minus I omega t sigma plus plus e to the plus I omega t sigma minus. Okay. If you were to rewrite sigma x as sigma plus I, and this as sigma plus minus divided by I, you do it, you get this out there. Okay? Notice what this does. This thing takes me from spin down along z to spin up along z, and this does the opposite. Everyone clear on that? So I can think about this term as sort of associated with absorption. The thing that takes me from the ground state and takes me to the excited state, and this term associated with emission, the thing that takes me from the excited state back to the ground state.
Are we still in the Schrodinger picture, or did we?
Sure we are,
Okay.
but we have a time-dependent Hamiltonian.
Okay.
So it's in the Schrodinger picture. The Hamiltonian is time-dependent, not because we're in the Heisenberg picture, because the thing that parameterizes the energy is classically time-dependent, because the magnetic field is time-dependent. So, excellent question. It is very confusing. Yeah.
Sorry, I think I missed. How did you get from the cosine omega t polyx to the bottom line?
I plugged in sigma plus sigma
Oh, I
minus,
see. Thank you.
and I plugged in sigma plus minus sigma minus over I,
Oh, I see.
and then I did the algebra.
Okay, thank you.
Yep. Mhm.
You're saying this term, e to the I omega t, sigma hat minus, contains essentially the emission statistics, but are you saying like it's like stimulated emission, right?
It is. I mean, we'll come back to that whole story about stimulated.
It's spontaneous.
And it's funny. Yeah, we'll come back to that. It's
Yeah,
very,
yeah,
it's
that's
very
good.
confusing.
Yeah.
Hold on to those thoughts.
All right.
Okay. Okay. So, as I said, in a kind of old-fashioned way, to think about absorption and emission here, and often what we think about is a kind of quantum jump picture where I absorb a photon, and I started here, and then boom, I'm here through the absorption. And if you had a standard textbook like I had, you learned about Fermi's golden rule, right? Professor Gold or whoever you had teach about Fermi's golden rule. And, you know, and then you have the rate of absorption is related to the matrix elements that start you in the initial state, get you to the final state. So this is, you know, equal to or proportional to the matrix element that takes me from the ground state to the excited state, the matrix element squared with some crazy density of states, you know, at the frequency. This is sort of the way, you know, Fermi and people from the 20th century thought about absorption. And this is missing the whole story when we have quantum coherence. This is a very incoherent picture because when they did this, they didn't have no lasers. They had lamps and they had spectral densities, and it's complicated, and we can think about it. But when I have something like a maser or a laser where I have to think about coherence. And this is a picture where there's no coherence. I started here and then I'm here. I was never in a superposition of these two states. But that's not the right picture in general. And we will now do that, okay? So, let's thus now try to solve this. We already did it. We already solved this problem in the Heisenberg picture, but now we're going to do it in the Schrodinger picture. Yes, Don?
You said the wrong way to think about it is that we started in an exclusively one state.
And then we ended up in a final state, and we never were in a superposition of the others. And when we have coherence, as well, and then we'll have, when we don't have coherence. Okay? So, in spin magnetic resonance, we definitely have coherence. Okay? Like in an MRI machine. Okay. So let's solve this problem by solving the Schrodinger equation. We solved it in the Heisenberg equations of motion. Now we're going to solve it in the Schrodinger picture. So what is the Schrodinger picture? The Schrodinger picture says the rate of change of the state. Oh, I mean, in principle, I could. Okay, maybe some of this. Where h of t is equal to h0 plus the interaction Hamiltonian as a function of time, right? So the Fermi's golden rule picture was kind of time-dependent perturbation theory. That's how it's often framed. But we're going to solve this problem exactly with no stinking perturbations at all, okay? We can solve this exactly for this particular problem. So how do we do it? Well, it's generally hard, and this goes, Tristan, to your point, to solve. Okay, so let me ask you all. So we just said generally, I can, in principle, write the state at a later time as this. Right? That's generally true. But what is U in this case, given a time-dependent Hamiltonian?
Take your interaction. Should be the exponential of the interaction.
So, okay, here's what Alejandro suggested. It's a good suggestion. Is this correct? Exactly. No, it sure doesn't, because it's pointing along X and then it's pointing along Y. So, good try, but it's not true. We have this horrible thing that's called the time ordering. That's script T, if you know what the heck that symbol is. And that's hard. really hard to do. I mean, the story of Feynman diagrams and the rest is all about that.
Do we move into the interaction picture?
Exactly, something close to it. We go into the rotating frame, which is very similar to the interaction picture, but not the same as the interaction picture. Because in the interaction picture, we go into a frame that's rotating at the natural resonance frequency. But now what we're going to go into is, just like we did here, we're going to go into the rotating frame, the frame that's co-rotating around the z-axis, so that we go into a frame such that the Hamiltonian is static. If we go into a frame where the Hamiltonian is static, then we can just exponentiate it and we're done, okay? And because we have this rotating field, we can go into the co-rotating frame, and in the co-rotating frame, the magnetic field is static, and thus the Hamiltonian is static, okay? So we're going to go to the rotating frame in the Schrodinger picture. We start from the Schrodinger picture and then go to a new picture, not the interaction picture per se, but the rotating frame picture. So the state in the rotating frame is related to the state in the Schrodinger frame. I have to do a frame transformation. That's a passive rotation, and a passive rotation, I should have called this, by the way, because it's a notation I like to use somewhere. That this is the Wigner D matrix along the direction n by angle theta, okay? So that's going to be my notation for a rotation matrix, and I have to go d dat, this is a passive rotation, and I'm rotating by an angle omega t. This is in the Schrodinger picture, okay? So this is how I go to the rotating frame. The operators, when I go to this new picture, it's a picture frame. Very good. Then my observables in the rotating frame are rotating by the unitary transformation. So that expectation values are the same. So I'm taking some of the time dependence out of the state, which would be evolving according to the full Hamiltonian, and putting it into the operators. It's like in the Heisenberg picture, you put all of the time dependence in the operator, and you take it all out of the state. In the interaction picture, you take usually 0. This is a different picture. Yes?
Does the z in the subscript just mean?
Rotating around the z-axis. So this operator equals e to the minus I omega t over 2 sigma z. Okay, because that was the general form. Sorry, Farouk. Oh, here it is. Okay, yeah. Excuse me, sir. Yeah, I'll get to you in a moment. Yes.
Because these are rotations, does that mean that the complex conjugate is the negative angle?
Yes, that's correct. In this case, it would be rotating the other direction. It's like time reversing. Yeah.
Rob, maybe I missed something. How do you move from the derivation of the interaction picture of the Hamiltonian down to now we have the expression for the Rabi alpha?
Okay, I'm sorry, you need to repeat the question.
How do you move from here to here?
No, this I didn't move. I just said I was just reminding you, those of you who have taken graduate quantum mechanics may remember Fermi's golden rule. So Fermi's golden rule is derived based on time-dependent perturbation theory where we talk about absorption and emission, and if I have an oscillating field, this is the usual picture. We have the square of the matrix element. That's all. I'm just reminding you about Fermi's golden rule. All right, let's now ask ourselves, what is the equation of motion of the state in the rotating frame? Okay. So this, in the Schrodinger picture, is the time evolution operator that we said. It's time t equals 0. Okay. So let's look at the equation of motion for the state in the rotating frame picture. So that's going to be equal to, well, I have to take the time derivative here. So that's the derivative of d dagger u plus d dagger omega t du dt by 0. Okay. Just using the rules of products and derivatives. So now, what I see is the derivative of the first term there. In the rotating frame. This guy is equal to plus I omega naught sigma z over 2 d dagger u size 0. That's the first term. Everyone see that? When I took the derivative, it brings down the exponent. Plus d dagger, and the derivative of that is the Schrodinger equation, minus I over h bar, the Hamiltonian u. So the time evolution operator, u, evolves in this way. The time derivative of this is this, where this is the whole Hamiltonian.
Just making sure. So that means that you're defining dz as e to the minus I omega naught t over 2. So that's it.
Oh, this should not be omega naught.
Yeah, omega,
Yes,
right?
yes, thank you, thank you, thank you,
No
thank you.
problem, no problem.
Omega, not omega naught. Absolutely, that's important. Yep. Good. All right. So now I can say this is psi of t in the rotating frame picture. And this over here, I'm going to insert a d dagger, because d is unitary, I can do that. Okay? And then, when you put all that together, and you do all the algebra, and you get the following. Where h in the rotating frame is d dagger h of t d minus omega over 2 sigma z times h. I'll let you do that algebra, but I want to focus on the result and not the algebra. So, what do we see here? What we see is, in the rotating frame, the state evolves according to a new Hamiltonian. The new Hamiltonian is the Hamiltonian in the rotating frame, which is what? It is the rotated Hamiltonian. This is the Hamiltonian that has been rotated at around the z-axis at frequency omega. But we've also added another term to it.
Does that correspond to Coriolis?
That's exactly what that is. So when you go to the rotating frame, there is an additional pseudo force. This is of the form minus gamma some a fictitious magnetic field dotted into S. The fictitious magnetic field is such that this is equal to h bar omega in the z direction. Okay, so going to the rotating frame is like adding an additional magnetic field along the direction of the axis of rotation. Okay, this is because we went to a rotating frame, this effect of the kind of Coriolis force is this, and this is an effect of Lorentz precession. And it's in the minus direction because we went into that frame. Okay, what about this? What is this unitary transformation? Well, this Hamiltonian, h as a function of t, was, what did we have? Where's the Hamiltonian? Is it somewhere? Where's my Hamiltonian?
I think you plug your interaction.
Here it is. Here's my Hamiltonian, that's h naught, and then I have the interaction Hamiltonian. So I have h naught over 2, that's h0. And then I have plus h bar omega over 2 e to the minus I omega t sigma plus e to the plus I omega t sigma minus. And then I have to subtract the pseudo or the fictitious magnetic field. Okay. This is my interaction Hamiltonian, the interaction with the, everyone with me? Okay, so let's do the unitary transformation. Oh, well, this is not. This equals that. Okay. So, what is the Hamiltonian in the rotating frame? Is equal to well, I have to take the unitary. Firstly, this guy, what happens to it when I rotate around the z-axis? Nothing, right? Because that commutes and it doesn't do anything. So what I have is that this thing equals h naught plus h bar times the Rabi frequency over 2 e to the minus I omega t d dagger sigma plus e to the plus I omega t d dagger sigma minus d. I have to rotate those, right? How am I going to do that? Well, here's a trick-a-rooney. Sigma plus, we said, was this. Okay? And D, in our case, is that, right? So when I conjugate this, I'm gonna get e to the minus I omega t over 2, and then I'm gonna get the conjugate, it's gonna give me another minus I. So what is true when you do this trick is that when I rotate the Paulis that are sigma plus and sigma minus around the z-axis, I get an e to the plus or minus I omega t sigma plus or minus. So when I do that, I cancel time dependence. And so this thing equals, so that tells me that the Hamiltonian in the rotating frame is in fact time dependent. I mean time independent. And I get h bar times minus omega naught over 2 sigma z plus h bar omega sigma plus sigma minus over 2, which is sigma x. So, in the rotating frame, the Hamiltonian, when I take into account the fictitious magnetic field, has this form. It's time independent. It's time independent because I went into the frame that was co-rotating with the frequency of the drive. Slightly different from the interaction picture. But it's quite similar. But it's not, if we went to the interaction picture, we wouldn't have gotten rid of the time dependence. And this has the form of h bar times the effective, where this vector, the effective Rabi frequency, has an x component and a z component. Bless you. So, let's put it all together. Let's look at what's in this box. What's in this box, it says, in the rotating frame picture, the state evolves according to this Hamiltonian.
The pseudomagnetic field that you said is what we call recent.
The pseudomagnetic field that we have, the fictitious magnetic field, came from this term. It's equivalent to what we saw classically as the Coriolis effect. But we just, I didn't do anything. I just went to the frame and I took the derivative and it came out of the algebra. It just appeared appropriately. So, let's put it all together. When we put it all together, we said that in the rotating frame, the state evolves according to a modified version of the Schrodinger equation with a new Hamiltonian that's transformed into the rotating frame with the appropriate fictitious magnetic field. And this Hamiltonian is written here. So, in the rotating frame, we have a time evolution operator. And we take at time equals 0 the Schrodinger picture to be the same as the rotating frame picture. So now I ask you, what is this time evolution operator? It's the exponentiation of this. We don't need no time ordering and integrals and anything, which is really, really hard. This one's really, really easy because it's static. Now we can just exponentiate the Hamiltonian. So the time evolution operator in the rotating frame picture is e to the minus I over h bar, that. And here's my Hamiltonian. So I plug it in. Yes?
In this picture, does the Rabi frequency correspond to anything physical?
Sure it does. Exactly the same thing as it was before. Let's think about it. Let's look at this together and think about what this physically means. So my first question for everyone here is, what is the nature of this time evolution operator? What would you call this kind of operator? This is a rotation operator. This is an SU2. Let's look at the simplest case to start. Let's say I'm on resonance. On resonance, omega equals omega naught, which means that the detuning is 0. In that case, omega effective is equal to omega, which in the rotating frame is along the x-axis. So in that case, what is the time evolution operator? Well, it is e to the minus I omega, capital omega t, sigma x. What is that operator? It's a rotation operator around the x-axis by what angle? Omega t. Not omega t over 2, omega t. That's the angle. Okay? So this is exactly what we said. So that means that if I started the system in the ground state, which in this case is spin down along z, then the state at a later time is this rotation. I mean, this is cos omega t over 2 times the identity minus I sine omega t over 2 sigma x. Right? That's the rotation matrix. So if I take this operator and apply it to spin down along z, what do I get? I get cosine omega t over 2 spin down minus I sine omega t over 2. And when I act sigma x on spin down, what do I get? Spin up, right? Because sigma x is equal to sigma plus plus sigma minus, and sigma plus turns spin down into spin up. So what's happening to the spin? In this case, it's rotating on the block sphere in the rotating frame. It started spin down along z. And if x-axis is out of the board, it's a lot more processing to spin up along z. How much time does it take to go from spin down to spin up? Well, it rotates with that angle. So when omega t equals pi, I have flipped the spin from spin down along z to spin up along z. Guess what that pulse is called? It's called a pi pulse for that reason. But what happens if I turned on this for half the amount of time, such that omega t is equal to pi over 2? That has a very fancy name. It's called a pi over 2 pulse. And what is the state of the system when I've allowed the evolution to go on for this amount of time? When this is pi over 2, right? This is equal to, this state is pi over 4, cosine of pi over 4 is 1 over root 2. This is 1 over root 2 times spin down minus I spin up. Now that's kind of a weird way of writing it. I'm going to factor out the minus I and then write it as spin up plus I spin down over root 2. Along what direction is the spin pointing here? The y direction, which is exactly right? Because this is spin up along y. I'm processing around the x-axis, and around the x-axis, if I start along z, I'll get to spin y, okay? Notice, this is coherent evolution. The system started in the ground state, but it didn't just jump into the excited state. It continuously evolved, and at every time is in some superposition of the ground and excited state. And intermediately, it's in a superposition. And at this time, halfway, it is in an equal superposition with a particular phase that was very well chosen. Okay? And what happens if I allow the evolution to continue past pi? Well, it'll continue to process, and it'll go back to the ground state, and on and on and on. If I had no damping, it would continuously oscillate between the ground state, the excited state, the ground state, the excited state. And so, in this case, the population, if I ask what is the population in, and we'll come back to Fermi's rule and stimulated emission. I'm sorry?
According to this block spin,
Yeah.
that means if you are introducing pi over 2 poles,
Yes,
you are taking it from x to y.
that's right. And
Which is
y
the
is
same
an
as
equal
opposition.
superposition of up and down.
Okay.
So whenever every state is some superposition of spin up and down along z. Spin up along y is a 50-50 superposition,
Between spin up and spin
but with a particular phase. So the pi over 2 pulse we do creates superposition with a special phase.
So my question now is, what is the difference between the normal superposition we normally have with this one?
The
The normal superposition we normally have, or we normally have with this one. What is the difference? Because you are saying now that introducing pi over 2 poles give us spin up along y.
Yeah.
And that spin up along y is the superposition between the two states.
Yeah.
With some well-chosen phase.
Correct.
That phase now, what is the difference between the superposition we normally have before we come to this particular expression?
Well, I mean, at an earlier time, so somewhere here, I have other superpositions
Yes.
with the amplitudes here that are not necessarily 1 over root 2.
Exactly.
So I will process the block vector processes around the x-axis and is pointing along a different direction, which is to say it's a different superposition. Yeah.
So when you write up Z and down Z, these are all up Z, down Z in the rotating frame, correct?
Everything is in the rotating frame.
Okay.
Yeah, because this whole thing is rotating around actually at omega naught.
So in the not rotating frame, in the certain picture, it would look very.
It will be rotating around, but we stay in the rotating frame, and we do all our measurements in the rotating frame, which we will get back to. But I want to continue with one more point before we end, okay? And then we'll take more questions. So I want to ask you, what is the probability to be in the excited state as a function of time for this problem? sine squared. Which is 1 minus cosine omega t over 2. Okay? So, if I were to look at this as a function of time, the probability to be in the excited state as a function of time looks like this. Where at time t equals 0, since I started in the ground state, the probability was 0, but at a time of pi, my probability is 1. And intermediately, I may have some other probability at pi over 2, my probability to be in the excited state is a half. These kinds of oscillations are known as Rabi oscillations. And sometimes this flopping from up to down is called Rabi flopping, kind of what rabbis do. But that's a joke for you, Dave. Rabi flopping is flopping up and down, but it's going in a way that is coherent. Intermediately, I'm in a superposition. And the ground state is doing exactly the opposite. So the ground state, the ground state starts here and goes here. Okay. And this kind of Rabi oscillations is the signature of coherent control. The fact that we can coherently control, we can create a quantum position requires this kind of well-defined frequencies in the problem. Yes?
So at the pi over 2, pulse, that means I have equal probability of being in the ground or the excited.
That's correct. That's what we just said.
Right.
Right here.
Yeah.
So
Exactly.
at pi over 2,
Yeah.
my probability amplitude is 1 over root 2 and I over root 2. And so my probability I have equal probability of being in the ground and excited state. I can't say. But over time, it would oscillate. Final question before we quit. What happens if I'm not on resonance? Just looking at this expression, where this is my omega effective.
The more it becomes insufficient to express it.
Well, in that case, what is this operator? It's a rotation operator, but around what axis am I rotating? On resonance, I was rotating around the x-axis. If I'm off resonance, well, I have my vector has an x component and a z component, right? This vector is omega effective times some. This is its magnitude, and this is its direction. The magnitude of this vector is the square root of omega squared plus delta squared. And the direction of this, well, it's x over that minus delta over that. That's the direction. That's a unit vector. And so I can't draw it in the board, so I'm just going to rotate the x-axis over here. So in that case, if I'm off resonance, let's call this the x-axis. The z-axis is here, and the y-axis into the board. And I will Rabi oscillate like that. It's the same problem. We solved it in the Heisenberg picture. Now we just solved it in the Schrodinger picture because and what we will find in that case is that the maximum probability to be in the excited state is no longer 1, because I don't get all the way to the North Pole. The probability to be in the excited state is less than 1 for finite tuning. And moreover, the oscillations happen faster. that's off-resonant Rabi oscillations. All right, I'm way over time. We gotta let the next class in. I'll take all your questions outside. Thank you.
Can I just ask my